All right, so listen, welcome to the Department of Long Overdue. We are at the SETI Institute. My name is Bill Diamond, the CEO of the SETI Institute in Mountain View, California, and I'm joined by John Richards, who is a software engineer, who is the guy that runs the Allen Telescope Array in Hat Creek in Northern California, about 5 hours from here. So the reason I said this is so long overdue is we've been doing Facebook Live for what, I don't know, over a year now. Almost every week we've been talking about all kinds of science and programming from the SETI Institute, from education to Sophia flights to astrobiology to exoplanets and everything. We haven't spent much time talking about our namesake activity, which is
the Allen Telescope Array
and SETI research. So this is really long overdue, but great fun to have John here, because of course he's normally up at Hat Creek, or he's at his base, which is out near Sacramento, because he can operate the telescope remotely. But we've got a couple things in the background I want to show you, and then John's going to kind of give you a guided tour of the array and the kinds of things. We're going to talk a little bit about some of the projects and SETI research we do up there, including that cool thing we did back in December.
So should we do an intro about
what? An intro about maybe the array itself, the dishes, maybe explain what a feed is so people understand what they're looking at here, and then we'll get into the site itself and what it really looks like.
All right. So I'm John Richards, and I work at the Allen Telescope Array. So it's in Northern California, way out in what I call the middle of nowhere. It's sort of near Bernie, California, or near Redding.
It's near, also it's like right between Mount Shasta to the north, Lassen Volcano Peak to the south, and it sits on about a 4,000 foot plateau of volcanic rubble, right? And as you say, in the middle of nowhere, beautiful, beautiful and desolate.
When you're standing there on to the north, you can see Mount Shasta. To the south, you can see Lassen. So it's a really pretty place. What we have there are 42 dishes, radio receiving dishes. And each one of these dishes is about 20 feet in diameter, so it's 6.1 meters in diameter. So
there's a model of one here.
Here's a model of one. This is what they look like, if you can see. So we have
come in and take
42 of these, looking at an object in the sky, trying to see if there are radio signals emitting that are signs of ET. Okay, so 42 of these type of dishes point at the same object. The energy comes from the sky and is reflected and focused off this big main dish onto this antenna.
Well, first to the secondary dish, right? So they
first primary dish, secondary dish, and then it's focused.
Show the antenna there, Lee.
On the antenna. Yeah. So that's what each one of these 42 dishes has in it. And this dish, or this antenna, is basically like the radio antenna you'd see on somebody's roof, but it's more jazzed up than that. So here's an example we have right next to it, one that was actually in one of these feeds.
So it gives you a sense of how big they are. So that's more than half my height, and so you can see it to scale on the model here. So, you know, as John says, these dishes are very big. Each one stands about 3 stories high. They're about 6 meters in diameter. And this is what we call the first generation feed, which started at, what, 500 megahertz or less?
Yeah, so down here is the tines for receiving around 500 megahertz, which is amateur radio. Then here's cell phones at like 800 megahertz, and then various spacecraft, and the spacecraft that NASA sends up, they broadcast from outer space, you know, and are received by these tines up here around 8.4 gigahertz. So,
and a lot of radio astronomy, classical radio astronomy, where they're basically looking for atomic signatures like helium, hydrogen, etc. Those are down around 1 to 2 gigahertz.
Right.
So they're down.
Right. They're down in the lower range.
So one of the things that separates the Allen Telescope Array from traditional radio telescopes is it has a bandwidth, it has a frequency response which is much larger, because we're interested in a broader part of the radio spectrum.
Yeah. So we can any given night we can observe from 1 gigahertz to 10 gigahertz, which, if you're not into the radio jargon, that's a lot of bandwidth to observe every night for such a small antenna.
Mm-hmm. And I don't know, Lee, if you can get close enough, but here's kind of the business end of the so-called feed. So John has referred to this as an antenna. We also call this a feed. And there's a little tip which basically takes the radio signals that are picked up by the tines and converts them into an electronic signal. It's what we call the low noise amplifier. So it's a tiny little chip, and that gets connected to the electronics at the back end of the telescope back here.
Yes, the main an interesting thing about this feed is that the signals, as he was saying, they travel, the energy travels up this copper into this tip, and then there is inside here there's a circuitry called a low noise amplifier, and it's in a device called a Dewar, which is cools it down, the electronics inside of that cools it down to 65 degrees Kelvin, which is less than 200 degrees Fahrenheit.
Colder than liquid nitrogen. So if you've ever gone to the doctors and they've used liquid nitrogen to treat something, it's extremely cold, and this is colder than that.
Yeah, we use the term cryo-cooled, which
Yep.
sounds really technical.
And John, explain why the pyramid shape. So what's with the four different sides?
This actually has what we call polarizations, which means we have an antenna, dual antennas that are pointed this direction, then that direction. So we can actually see different characteristics depending on what transmitter we're receiving from. So we call it the X pole and the Y pole.
Mm-hmm.
So it's a dual pole antenna.
Yeah. And what we've done, I think John will probably show you some pictures, but this is what we call the first generation feed. And the cooling that John mentioned is kind of inside here. We were interested in moving to higher frequencies in terms of the bandwidth. So being able to go up to 14 or 15 gigahertz.
Yeah, 15 gigahertz.
And we were also interested in being able to cool down the entire feed, not just the electronics. And so we sacrificed a little bit of the low end bandwidth. I think now the new feeds start at a gigahertz.
Yes.
And they go all the way up to 15 gigahertz, so it gets even tinier up at this end. And the entire feed, as you'll see in the pictures later, is under a glass dome on a big box of electronics and a cryogenic cooling mechanism, or cryo pump, that allows the whole mechanism to operate at the same temperature range, around 65
Right.
Kelvin. And that just means that you have less background noise to deal with, because thermal energy equates to noise in the radio spectrum. So you have a better signal to noise ratio, better sensitivity, better performance with these new feeds. So that's why this guy is now, part of the museum collection.
Yeah.
And the new feeds, we want to acknowledge are a result of a benefactor that we have, who has both been extremely interested in the technology of the feeds and the antennas themselves, because he has a background in this area, but has also been generous enough to fund both the development and the production of the feeds. And this is a gentleman named Franklin Antonio from a very well-known chip company in the United States called Qualcomm in Southern California. He's one of the co-founders of that company. And the new generation feeds are called the Franklin Antonio feeds, or the Antonio feeds for short, in honor of Franklin, who funded their development, which was quite a project. We're still working on some of the finer elements of that design, but we're very grateful to Franklin for having supported that upgrade of the ATA.
We have a video of it on the screen here right now.
Let's, you want to take a look at that? Let's do that. So maybe we start that again.
Yeah.
So what you're looking at before you, even while you're playing it, you're looking at the inside of this area. So in the Allen telescope array, this is covered by fabric so that we can protect the electronics from the sun and from
Squirrels.
dirt and dust and squirrels and other things. So you're seeing actually John inside the feed. He's not always there, although probably sometimes feels that way. So John is inside this area, which gives you an idea of how big it is. It's almost like a small room, and he's been working on the feed. So we don't have a person behind every feed and every dish, but you could think that when you see John emerge from this one.
Yeah. So
but that's what it looks like. So
here's the large glass bowl. So instead of, as we explained here, how there's a Dewar that's inside cooling the electronics down to 65 degrees Kelvin, instead of that, we cool everything. So this inside of this glass is a vacuum. So inside of all this glass, everything is cooled down to 65 degrees Kelvin. And one of the things you might notice how shiny these are. Well, they always stay shiny because
protected from the elements.
One of the things with a vacuum, there's nothing in there, so there's nothing to corrode the nice copper. And this one right here, this is one of the original ones. It's been shined up. They don't look this good after a couple of years because it's copper, so it automatically.
It oxidizes.
Yeah.
Sure. Yeah. So they all look pristine now. And so John, why don't you grab a seat here, and maybe you can explain as well how we get the signal, the electronic signal at the back of each dish onto, well, into our computers in the processing center or the control room.
Okay, so if you want to go back to this model again, so this is, like I said again, basically the antenna, and the antenna wires, just like in your house, but of course more advanced, go from the antenna all the way up through here, down the mast, and through these large PVC pipes to our main building, our main computer system. So we have, like I say, we have 42 of these dishes, and so we have a bunch of pipes running underground. You can't see them when you visit the site because they're underground. All coming in via fiber optic cables into our computer system.
And this is our, so each one is on a 10 gigabit feed, is that right?
Yes.
Optical feed.
Yeah, optical feed. Yeah.
Which is fun for me because that's the industry I came out of, the optical networking industry, making lasers and transmitters and receivers. So it's fun to see them in action, supporting the SETI research at the Allen Telescope Array.
So the optical has to be converted, it's light waves coming in over fiber, has to be converted somehow into a signal that the computers can actually chew away on. So the light is actually converted to voltage signals. There's a converter for that. And then from voltage signals, it's digitized. And once it's digitized, that means it's in the bits and bytes that the computers can operate on.
Yeah. So, by the way, speaking of liquid nitrogen of 65 degrees Kelvin, some of you out there watching from the upper Midwest of the United States have been dealing with some unbelievably serious cold. So if any of you are out there watching, we often have people watching from Chicago and Minneapolis and so forth. If any of you have been dealing with the polar vortex, let us know where you're calling in from, or sorry, watching from, and what temperature it is now, and maybe what the coldest temperature you saw over the last 24, 48 hours. First of all, we hope you're all safe and warm. It's been an unbelievable weather phenomena, but be interesting to hear from any of you who are in that part of the country. And of course, we always like to hear from our friends all over the world, so let us know. And we've got Rebecca here taking questions, so if you've got questions about the ATA, about our SETI research for John, then fire away, and we'll start taking a look at those. And in the meantime, John, you've got some other, I think, videos here that you'd like to share.
Let's see. Here's a really nice one of, we had a gentleman come out.
Get it full screen?
Yeah, I will. We had a gentleman come out, and he has this camper that you can see in this video right there.
Oh, that's great, because that gives you a sense of scale.
Yeah.
And this is not the control room, by the way. Yeah. This shed is, just tools and supplies. But so the control room is kind of from the perspective of where this shot is taken. But that's how big a van and truck is compared to the dishes.
All right. So while we're looking at this picture, these are actually what we call a node house. We have 5 of these around, and what these are actually inside. This is not a chimney. It's actually an air vent where air is sucked down into these, and then through the ground, the air is forced up through these masts to keep the dishes or the antenna computers that are inside of the actual dishes, to keep them cool enough, especially in the summertime.
Yeah.
So these are humming along at all times, and then the signals come from each one of these dishes into a node house, and then the node house has these big PVC pipes that go.
Now, in terms of the environment, what kind of temperature ranges are you dealing with at Hat Creek, from this extremes of summer to the extremes of winter?
I'm talking Fahrenheit here because we're in California, but I've been there when it's been 108 degrees in the summertime, and that's rare. But we probably get over 100 degrees, maybe a couple 10, 20 days a year. And then I've been there in the wintertime where it's been 5 degrees Fahrenheit. So that's
well below 0 Celsius.
Yeah, but it's not too hot and too cold most of the year. Yeah, and we don't get too much snow, but we get enough to make it interesting. Yeah. So this gentleman, he came out and he was doing astrophotography, and what that means is he parked his car there, and he actually had his antennas or his camera sitting up on a little hill on the side, and he exposed each picture, I believe, 20 seconds, so you can get a lot more light coming into his camera. And this is what he came up with. I thought quite interesting. So if you watch this,
See the dishes move.
so it's fast motion,
Sure.
time lapse. But the sun is going down behind the mountains here. It's getting darker and darker. There
There's
you
the
go.
Milky Way.
Milky Way
Okay.
just pops in, and with your eye, you could, if you've ever been out in the wilderness, you can kind of see the Milky Way. It looks fuzzy, but if you actually expose it, like your eye cannot, you see a lot more.
All the detail.
All the details up
Yeah,
there.
yeah.
Yeah.
It's beautiful, and one of the things that you can surmise from seeing this video is that, and you can look around in this picture, you don't see any other, there's no buildings and stores and shops and houses. It's the wilderness, and so it's very dark, beautiful dark sky sight, and of course, unfortunately, those are very rare places in the United States and in the world at large to have wonderful dark sky places to do observing, optical observing. The radio antenna don't really care, but they care more about radio noise, and of course we have large populations in metropolitan areas. You have radio noise. They don't care about the light noise, but people with telescopes do, and so not only is this a great place to do radio astronomy, but it's a wonderful place to bring up telescopes.
Okay.
And by the way, it's open to the public. If you live in California or Nevada or around here, or you're visiting out here, you don't mind a bit of a drive from San Francisco, you can go out there and visit the Allen Telescope Array. It's open to the public during the week.
Yeah, 9 to 3 every day.
9 to 3 every day.
Not on weekends and not on holidays.
So there you go.
Yeah.
But come and see. All right, and I think you've got some other shots here.
Let's see what else we got here. Another nighttime. This is done by Showstack, I think.
Yes, yeah.
Yeah. So you can see a lot.
Those are airplanes flying by. Yeah.
Well, we think they're airplanes.
You're not
Yeah. So it's very pretty there at nighttime.
Yeah,
Yeah.
absolutely.
It's very quiet, and sometimes if you have a really cloudy night, you cannot see anything out there at nighttime.
Now the Allen Telescope Array generates a lot of data. Each dish is pulling in a lot of information. As John was saying, they're all coordinated, so they're all looking at the same object in the sky at the same time. But I think it's pulling in something like 54 terabytes of data every day, on average. And so it's massive amounts of data. We try to process the signals in real time, because if we saw something interesting, we would want to immediately alert other facilities in the world to train their telescopes on the same phenomena and see if they can verify it. But if we want to look at the data with maybe more advanced machine learning and artificial intelligence tools and algorithms, that might help us see things that our real-time processing is not capable of seeing, patterns that might be in the wideband, or anomalies in the signal that normal data analysis can't detect. You need additional tools. We've been partnering with IBM now for over 2 years, I think. IBM Research had approached us because they said, we're developing the latest generation machine learning and AI tools and algorithms, and we're looking for large and interesting and multivariable data sets. We know the Allen Telescope Array generates a lot of interesting data. If we could get access to that and use it for helping to train our algorithms, we would in exchange give you access to our AI tools. So we immediately said yes. I think it took a nanosecond or so for that decision to be made. And so we've been partnering with IBM Research now for a couple of years, using their advanced machine learning tools in addition to our real-time processing. And so last December, we had some real fun, because Robert Downey Jr. of Iron Man fame is producing a documentary series called The Age of AI that's going to be coming up on I think YouTube Premium or Premiere sometime later this year. And it's a whole series about the application of artificial intelligence to things in life, medicine, cars.
But we didn't get to meet Robert.
We did not. He did not fly in.
Everybody was there except for him.
Yeah, we had a huge film crew at the Allen Telescope Array, because we were demonstrating the application of AI and machine learning, and how we use it for SETI research. And John, why don't you tell them what the event was that we wanted to witness with the Allen Telescope Array, why it was interesting, and how we did that.
Okay, so here I got a graphic here on the screen here. We had a situation on the December 10th, 2018. This is when the film crew was here.
There.
Yeah, sorry, there. Yeah, down the telescope array. Yep. It was kind of to celebrate that a conjunction was happening. So this is one of the solar systems discovered by the Kepler program, and they've discovered this solar system that has 7 planets that are fairly close to their sun, their star, but theirs is much smaller than ours, so
it's
not
a red
as
dwarf
hot.
star.
But they're closer than our Earth is. So they determined that there are 3 planets in this solar system that could potentially have the right conditions for life, meaning it's not too far away to be too cold, not too close to its sun.
That so-called Goldilocks zone,
Goldilocks zone,
habitable zone.
It's just right, yeah. So on December 10th, there was a time in which if you were on Earth and you were looking at the TRAPPIST-1 solar system, you would see 2 planets actually line up with your line of sight. So actually the second planet you would not be able to see because the first one would be in the way. So this is interesting in the radio spectrum because just like in our solar system, if, let's say 10, 20, 50 years from now, there's going to be a lot of activity, hopefully humans, on Mars. Well,
there's already machine activity on Mars, right? So and we're communicating.
We're starting to blast signals towards Mars to communicate back and forth, right? So the theory is that in 50, 100 years, there's going to be a lot of communication going back and forth, really blasting. Well, we're thinking if they were advanced enough, if they were in the same position like Earth and Mars, but they're 2 planets, and this one was broadcasting to this one, blasting signals like we will be to Mars, we would actually see overspill, and we would have a large radio signal of great power directed right to us on Earth. So
this would be like eavesdropping on their communications.
Yeah. So we, for an hour before this lined up, an hour afterwards, we gathered data to see if there was a power spike right when these lined up with Earth.
And I think it's fair to say, before anybody gets too excited, that we didn't expect to have a radio transmission where we could sense a message or least of all decipher a message. But the idea would be, do we see a difference in the radio spectrum and the radio signal before and after the alignment of these planets that might suggest there's some radio transmission traffic going back and forth. So I mean, it's an interesting idea because for decades, since SETI really commenced as an activity or as an endeavor in 1960 with Frank Drake, it's really just been a search for a needle in a haystack without really knowledge that planets are everywhere, which we now know, or what kind of planets are in what places and where habitable zone planets are. The SETI efforts have always been kind of just a random, let's point the telescopes at this star or at that star, not even knowing if that star has planets. Well, now we know, thanks to Kepler and soon TESS and other techniques, that planets are pretty much everywhere. Every star has them. But just like our own solar system, not all planets are created equal. Gas giants are likely not going to have any kind of advanced life,
but you never know.
You never know. We don't rule it out completely, but it's in terms of life as we know it, very unlikely. But now we're at a point in our technology and in the history of humankind where not only do we have the technology and the capability to look and listen for signs of technology and signs of life elsewhere, but we know where to look. That's what's interesting about this. So even though this is a bit of a long shot in terms of are there actually radio transmissions happening between these 2 planetary bodies, it's a logical construct. It's a logical place to look and a perfect time. Also interesting about this, because that planetary system is 40 light years from Earth, what we were observing at this exact moment of time actually took place 40 years ago. Yeah. So it's always kind of fun because SETI work is not just an adventure in space, but also in time. So that was fun. And so we had the film crew and we sent data down to IBM research colleagues in South Africa.
Still being analyzed.
Still being analyzed, still looking at that. And some interesting things have come back that warrant further investigation. Nobody's popped the bottle of champagne yet and said we've found technology, but some interesting things that warrant further investigation. And also, every time we do this, the machines get smarter. The machines begin to differentiate more effectively between signals that are interesting and signals that are not, signals that we should look at more closely and signals that we should discard. So, you know, the future gets brighter and brighter.
Right, so, you know, to that end, it might be worth explaining that we started building this site in around the year 2000. And the electronics and computers weren't as advanced as they are now. I mean, they were fairly advanced, but you couldn't buy the equipment in a store or anywhere to do a lot of this processing. So a lot of this computer that we have that does all this massive processing is custom made, and with devices called processing devices called FPGAs, and they're very expensive. They're very touchy, and it's hard to grow them because now it's old technology. So we're in the process now of trying to figure out how to upgrade our system and using off-the-shelf computers. You can get,
because now we have compute technology that's
and we have from the gaming world, we have the GPUs.
Right.
So the NVIDIA, those GPU processors are what is going to be used, I think, in the future. So in 5 years from now, the whole thing, the old hardware is going to go away. It's going to be these GPUs. And an interesting thing about the GPU is, remember, it became really popular like a year ago to do Bitcoin mining on these GPUs. That's what they used. So because Bitcoin became really expensive, right? So people were buying up these GPUs, and people in the astronomy world couldn't get them. They doubled in price. And not only they doubled in price, but it was hard to actually get them.
Just the availability.
But now that Bitcoin has slid down, nobody's interested in doing that anymore. So you can buy those GPUs now on eBay for really cheap. And now the new ones are down to a regular price.
So it's funny, it wasn't all about gaming, it was all about Bitcoin.
Right.
Interesting. Yeah, so we are in the process of upgrading the electronics on the back side of the array. Something else interesting to point out about the Allen Telescope Array, it is the only radio telescope on planet Earth specifically and exclusively designed for SETI research. There are certain characteristics about the way it's constructed, the way it tries to mitigate and get rid of radio frequency interference that could be nearby, the way it uses signal processing to differentiate between so-called RFI or radio frequency interference and signals of interest. So it's really exclusively designed for this purpose. And while SETI work is done on other wonderful radio telescopes like the Parkes Telescope in Australia, the Green Bank Telescope in West Virginia, and Meerkat in South Africa, etc., this telescope has a wider frequency range and again is really purpose-built for doing SETI research. And I think, judging by Lee holding the magic pieces of paper, that we got some questions that have come in, so let's throw out some of those.
All right.
How do you separate the different signals so you get a read of each frequency? So how do we separate the different frequencies? Might be worth talking a little bit about, I don't know, a waterfall chart or plot, or what the data actually looks like that comes off the array.
Yeah, so that's...
This is from, I'm not sure I'm pronouncing it right, either Sila or Sila, so thank you, Sila.
So hopefully I'll answer this correctly, but I like to think of it like a stereo, or in the car, how you'd be listening to it and you would see those bars. They call it the equalizer, right? So basically we're using the same process as that's being done. So we have the data's coming in, we digitize it, and we run it through this process.
So we can see the signal intensity across a wide range of frequencies, just like an equalizer would do.
Exactly like an equalizer, yeah. So like a stereo equalizer, if you saw one of the bars go really high, high strength, you know there's sound, there's a signal.
So there's a signal at that frequency, at that wavelength. Yeah.
So what we basically do is we run we run our data, which comes in the time, what we call the time domain, comes in, and we're digitizing it in time and converting that using a process called a fast Fourier transform. You can look it up on the internet, and that's
FFT.
It's the same basically how they do the car stereo equalizer, you know, the bars, and that converts it to frequency domain. So basically what you can do is you can look and see, hey, if you've got it now in the frequency domain, if one of these channels pops up and you got a lot of strength in there, you know you got a signal at a certain frequency.
Of course, that's the reason why we are interested in a wide range of frequencies. You know, a radio astronomy telescope that's just looking at how different atoms emit different radio frequencies as they vibrate, etc. And we can look at for hydrogen and helium and other things in space. We don't know what frequencies might be used to transmit information in advanced technology, so we're sampling across a wide range. And as John says, you have the ability then to see a particular frequency spike, and then we want to take a closer look. I think we already answered this question, but we can answer it again anyway. Deborah wanted to know if it snows at the ATA, and the answer is yeah.
Yeah, sometimes, maybe it's been like a foot. That's what I've seen it.
Yeah.
Not
So
like
we've,
that.
the other side of it is depending on how you get there. So I mentioned earlier that the array sits at about 4,000 feet, just over 3,000. What is that? How many meters is that? A couple thousand meters.
Yeah.
But one of the access roads coming in from the south takes you up over a 6,000 foot peak, so over a mile high. So you can have situations where even though it's not snowing at the ATA, you've got to deal with snow on the way in.
You can't drive home.
You can't drive home, or can't make it there.
The extreme weather we really have is sometimes we have windstorms. So there was one time where it was late at night, and Saturday night at 3 a.m. I heard bam in the house. There was a place to stay there. I heard bam! It woke me up. It sounded like something hit the house. And I actually went into the array, and what had happened is we had a gust that was so strong it destroyed the weather station and hurt some of the dishes.
Really?
Yeah.
Unbelievable. So actually the other thing that we're dealing with, nobody's asked this question, but the other thing we have to worry about up in that part of California are wildfires. Right. And there was one, what was it, 2-3 years ago or 4 that wasn't too far away.
Yeah, it was kind of scary. We have a webcam, and the very last photo before the fire burned the fiber, the internet fiber, was the fire coming. It's a very scary photo. I have it on the web somewhere. Yeah. But luckily, after it burned the fiber, we couldn't get there for a whole week because the fire department closed all the roads, and we didn't know what was going to happen. But luckily it didn't actually come on site, so we were safe.
Didn't go over that fire break, I guess.
But we have generators that kick on when the power shuts off. So we can actually keep observing. The whole system doesn't know that power's been shut down. But the problem with that, we have to fill up the tank every 24 hours, so it only lasts for a short time.
Unless somebody's there to refill it. So yeah, that's you've got to deal with real world scenarios there. Okay, so Danny is asking, I guess it's Danny, is asking the obvious question: any alien contact?
No. Sorry. So I get that question all the time. So the answer is, if we had contact with aliens, I wouldn't be here talking.
You'd know about it already.
Yeah.
Yes. Yeah.
Or it'd be so secretive, the government would come in, or I don't know what would happen. But so no. Sorry.
So I've been thinking about this lately in terms of all the press conferences we have in this country about people who are running for president in the future or things of that. It occurs to me that I wield an incredible amount of power in terms of the media, because I think if the CEO of the SETI Institute called a press conference, everybody would assume it was because the big news was out there, and I don't care who they were talking to, whether it was President Trump or the Queen of England. They would pack up their microphones and cameras and head to the SETI Institute pronto to not miss that. So suffice it to say, we'll use that power very carefully. If you hear about us having a press release, definitely pay attention. Otherwise, as John says, if we had made contact, you'd know it. However, maybe you could talk about the 6 levels of signal analysis that we do in terms of, something that looks interesting gets looked at a higher degree of inspection until it ultimately gets to a point where we do a human oversight or human observation of the data.
Yeah,
so there's a protocol of re-examining interesting signals.
So you have to keep in mind that we have a lot of radio frequency interference, which comes from cell phones, satellites, squeaky equipment, washing machines,
spacecraft,
everything. Yeah. And so the big job of the computer system is to once it's digitized, to analyze for signals and try to cut out the ones we don't want to look at, which are most of the signals. So we see hundreds of thousands of signals every night. we try to use some criteria to say which ones are we actually interested in. So we use this technique called the Doppler shift. And the Doppler shift is just like the effect of when a train is coming towards you with its whistle. You know, its whistle will go, woo, will actually sound like it's raising up. And then when the train goes past you and away from you, the pitch of the whistle goes down, right? So that actually is just radio signals do the same thing. Oops.
There it goes.
So with radio signals, if you see a radio signal that is not shifting in time, in frequency, if the frequency is steady, never shifts, you know that is radio frequency interference, because it's something that's coming from the ground and not moving towards or away from you, not accelerating towards or away from you. So our system cuts out all signals that are not drifting in time in frequency. Okay, so then we have some left over. And if the signal is too strong, we know it's not from ET. So it's just like blasting our system. Right? So we're looking for something really weak. So if we see something of interest, which we do sometimes, maybe every night or every couple nights, what we do is we immediately think, oh, this is probably a radio frequency interference. So what we do is we see it, and then we go off and we observe. We look off of it.
In other words, you steer the distance off of that point.
Right.
Okay.
And the theory is, if you see the same signal coming from two different locations, well, that's radio
then
frequency
you know it's
interference,
local.
right? Or it might be a fairly strong satellite coming in from the sides and drinking out the system. So what we do is, if we don't see it the second time, we go on again. If we see it while observing on, we go off and on, off and on. Mm-hmm. And if that passes that 5 times, I get an email, and all the data is stored in the database, and for all these instances on and off, all that data is stored on the computer system, so we can go back and look. So we're just notified that a significant event has happened, and then humans can go back and we look at everything and re-observe. So I've had this happen several times. I had it happen about 2 years ago, and I've had it actually happen several times. One time I had a parameter set wrong in some file, and it was kind of freaking it out. This last time, I actually looked at all the data that was saved, and then went back, and I was able to see it myself. And it was some fuzz coming off of some electronic equipment that was shifting in time, was shifting back and forth, drifting. The frequency was drifting, and it was so it was a signal that was tricking out our system. To pass the 5 levels.
How do you rule out that? How did you differentiate that? Okay, this is like a false positive, as opposed to this is actually maybe something interesting.
Yeah. So one of our criteria is a steady signal. So we're looking for just a steady tone, that's shifting in time. And this thing was we're looking for a narrow band. Right. So it's like a narrow frequency.
Like a carrier.
This was a fat fuzz. If you actually looked at it in this thing called a waterfall image, where we try to image this data. And you can see lines, and those are the signals that are coming in. We're looking for a line that's sloped because of the frequency shift. This one was a fuzzy thing, and it could have been, if it kept on going, if it was constant, but it actually, you saw it would drift back and forth. And it just happened that the second time we actually looked at it, it was drifting back at the same speed. So if I watched it over time, I could say, oh, this I think I was too close to the geo belt, which is where a lot of satellites are, and there just happened to be one that was flaking out the system.
Well, as John mentioned, so that's one of the things we have to deal with all the time, is the complexity of all the different radio signals that are coming in from a myriad of different sources in space, on the ground, and rule them out before we can say, oh, this is something of interest. I think it's worth saying, however, that Jill Tarter, and I think you've met Jill on our Facebook programs in the past. She's the woman who the character played by Jodie Foster in the movie Contact was based on Jill's life, at least the first half of the movie. And Jill famously describes the SETI endeavor as, well, how far have we looked? What kind of an investigation have we done? And she likes to describe it as if you walked on the ocean and walked up to the beach and into the water with a measuring cup, and you dipped the measuring cup in the water and you didn't find any whales, you would be wrong to conclude that there aren't any whales, But that's the equivalent. I mean, a measuring cup of water compared to all the water in the oceans is kind of a pretty good analogy of how far and wide we've looked for intelligent life beyond Earth. So, you know, these are the very early days of this endeavor. More and more instruments are becoming available, looking at all the sky all the time. We have a laser SETI project to look for the technology signature that laser light might produce. So the more instruments that we have on the sky in more places for longer periods of time, the more likely we are to find something. But you know, we're in very early days.
Very early days.
So let's see. Somebody else here. I'm not sure what the name is. Sagan or Sogan. Do you think intelligence as we know it exists either inside or outside of our solar system? Well, we've looked all over Earth. We haven't found any. Let's be clear on that.
Well, by inside the solar system, I guess there are theories. You know, that there is talk that we haven't really searched our solar system, and my thought is that would be good. That would be a good thing for a satellite to do if you. Someday in the future, when satellites become less expensive, to have something that would continually scan.
Sure. I mean, I think it's safe to say that there's certainly no signs of anything obvious in our solar system emitting, you know, what we'd call techno-signatures like radio signals or laser pulses. There is, I think, very reasonable speculation in the scientific community that there is life beyond Earth in our solar system, very likely on Mars at, you know, the microbial level, microscopic level, very possibly on Europa or Enceladus, these moons of Jupiter and Saturn. So there's, and you know, it's certainly possible that early on in its life, Venus supported biology. So lots of opportunities for life, at least at some level, in our solar system. Outside our solar system, I mean, personally, I'm convinced, because I think the statistics are overwhelming. You know, we, in our own galaxy, never mind that there are hundreds of billions of galaxies, but in our own galaxy, we now know that statistically every star has one or more planets around it. We know, again, statistically from the Kepler data, that about 20% of those are rocky planets, about, you know, plus or minus the size of Earth. Rocky is important because as a physical surface, the water can pool. So these are planets, rocky Earth-like planets that exist in the so-called habitable zone of their host star. The numbers that are projected based on the Kepler data suggest that the number of Earth-like rocky planets in the habitable zone of their star, just in the Milky Way galaxy, is a number in the tens of billions, 10 to 50 or 60 billion. So that's a lot of opportunities for life to have happened, a lot of opportunities for even complex and intelligent life to have evolved over time. You know, do we overlap in time in a way we can find one another? Do we use technologies that are similar enough for us to discover for each other? We don't know these things, but I think the science, particularly of the last decade, has made the search for ET more compelling than probably it's ever been. Let's see. Can we talk FRBs? Serge wants to know. Yes, we can. Tell them about fast radio bursts.
Okay, so my knowledge is sort of limited, except I know that we are actually in the process of developing a system, and hopefully it'll be up by summertime. Mm-hmm. It's been funded, and we're actually doing the install of the hardware.
And this is a partnership with Caltech, by the way.
Yeah.
And it's funded by the Mount Cuba Foundation, Astronomy Foundation. So very exciting.
So we're going to be using 10 of these dishes, and they will be wherever we're observing at any given time. There's a side process that's going to be happening that's going to be looking through the data for these fast radio bursts, or they're called FRBs. So these FRBs have become quite popular in the last decade, especially the last year, because they're extremely strong flashes of energy, bursts of energy that are coming from various parts of the galaxy and solar system, or the universe. Universe, other galaxies, and they don't know what could cause these type of radio bursts.
Right.
They're kind of a mystery, and they don't know where these are. So they have found several that are repeating now. So That's what we're going to be training our system on, is to look at the repeating ones and see the repeats. But that's one of the big things in radio astronomy now, is these fast radio bursts. Where are they? Why are they? So we're hopefully in the next decade, we're going to be discovering tens of thousands of these, hopefully, and we'll get enough science behind it to be able to explain what they are.
When John says they've become popular recently, it's not because they're a recent phenomenon, it's because we've recently had the technology to find them and see them. But just to give you an idea, so these are massively intense bursts of energy that we pick up in the radio frequency. They're very far away, so there's a famous galaxy called Galaxy 121102. There's a fast radio burst coming out of that galaxy. It's 3 billion light years from Earth. So it's 3 billion years old, the light that we're seeing, or rather the radio signal that we're seeing. The energy is massive, so we are calculating based on the energy flux that we're able to pick up from this fast radio burst, that burst has more energy in it, or as much energy in it, in 1 millisecond, 1/1000th of a second, as our sun produces in an entire year. So that's a pretty energetic divide.
And they have no idea what
we don't know,
produced that.
We don't know what natural phenomena produces it. We don't believe that it's an unnatural phenomena that produces it, but we don't know. It's not only the most exciting topic in radio astronomy, I think it's the most exciting topic in all of astronomy. All astronomy is really very curious about these objects. We years ago discovered things like pulsars and fast spinning neutron stars, and we're discovering new things all the time, quasars. But FRBs are truly amazing, very, very high energy, very, very far away. And we're seeing them in different parts of the sky, meaning they're not coming from like one galaxy, they're coming from different galaxies all around. And as John says, we expect to find a lot more, and really interesting will be the ones that repeat, because when you have a phenomenon repeating, you have a much better chance of understanding the mechanisms behind it. So yeah, FRB's cool, great question. Does this array use interferometry, or are they separate nodes? Skylar wants to know.
Yes, we use interferometry. We use, this array can be operated in 2 modes. Interferometry, which basically can be like a camera on the sky, and you can actually image bright objects in the sky, point sources, etc. And we have, on the web, there's some pretty nice pictures. They're low resolution because they're done in the radio spectrum, but instead of, your eye cannot see in the radio spectrum, so this kind of images what you can see with what you could see in your eye if your eye could see radio. But the other side of the spectrum, the other side of the aisle is the beamformer, which takes each individual antenna or dish, takes the signals and combines them into what they call a beam, so you can actually look at very small sections of the sky.
Yeah, at the same time.
At the same time.
Yeah, yeah. And we hope with other advancements in the electronics of the array to be able to add additional beamformers, so that actually we could look at 12 or 100 or even 1,000 multiple points at the same time. These are when we scale the operations in such a way as that finding a signal of interest, the probability just goes up and up and up. So don't think we have any more questions, but I do want to acknowledge the great list of guests we have from all over the place. I didn't see anybody here who's said they are coming from someplace extremely cold, although somebody's watching from Chicago. They just didn't say how cold it is there, but we've got Santa Cruz, California, not too far here along the coast. We've got Florida and Portugal, Germany, Brisbane, Australia, Texas, Genoa in Italy, Israel. We have Fort Lauderdale, we have Calgary in Canada, we have Barry in Wales, we've got Staines in the UK, we've got Virginia and Lille in France, we've got Brazil, Uruguay, Placentia in Belize. You're going to Belize tomorrow, right? Wow. So anyway, you guys in Belize, you can meet John. He's on his way to Belize. Chile, Opole in Poland, Glasgow, Scotland, Burgoyne, North Wales, it looks like, Roscommon in Ireland, Williams Lake, British Columbia in Canada, Clarksville, Tennessee, Chicago, Turkey, Durant, Oklahoma, Quebec City, Sri Lanka, New Brunswick in Canada, Louisiana, Sao Paulo in Brazil, Oran, Algeria, Austria, Macedonia, Charleston, South Carolina, London, Vermont, Grand Haven, Michigan, Hungary, Mexico, Belgium. So all this says to me is that, you know, what we're doing here is of universal interest.
Yep.
That, you know, curiosity is one of those human traits that unites everybody across the globe. We all share that no matter where we're from, no matter what background we have. It's wonderful to see all of you from all over our planet excited about the work we're doing here at the SETI Institute. Great to talk to John. Long overdue exploration of the Allen Telescope Array. We'll come back and visit that topic again. Obviously, if something big happens, you'll hear about it first here.
We should do this sometime from the array.
That would be good, but the problem is we'd have to do it at a point where we can get a signal, because you're not allowed to have your phones on. You're not allowed to have telephones on, and so. But if we're not observing, I guess we can turn on the phones if we can get a signal, and we can do video there. Yeah, absolutely. We could tape it and show it later. So we'll take you up there. That would be fun. You'd enjoy that. We can come back and talk about FRBs when we get that project really off the ground.
After we see the first one.
Yeah.
Hopefully in the fall.
Hopefully by fall. We'll have the equipment on the system this summer.
Yeah.
So we'll be starting that project. I want to acknowledge also Dr. Andrew Simeon, who is the Bernard M. Oliver Chair of SETI at the SETI Institute. He's based out at UC Berkeley, so he's not here with us today, but he's really in charge of our SETI research and works closely with John on the programs we do there. And, you know, collaborations we have with different organizations around the world in the SETI arena. So lots of exciting stuff. We'll come back and explore that more in the future, and yeah, get them up to the array. So that would be great. Thank you all very much.
Thank you.
Everybody in the polar vortex, please stay warm and safe, and we'll hopefully see you here next week for another Facebook Live. Do we know what we're doing next week yet, by any chance, Rebecca?
We don't.
Not yet, so it's going to be a mystery, but we'll let you know on our social media posts. For now, from Mountain View, California, thanks everybody for spending some time with us. Thanks, John, for coming and talking with everybody.
Welcome.
And we'll see you next time, everyone.
All right.